My name is Mehmet Ali Nazlı. I am a mechanical engineering student at Hacettepe University. Today, I will tell you about my electronic systems and sources term homework. My term homework is Ionospheric Communication. My instructor is Çiğdem Seçkin Gürel. Contents, introduction, abstract, ionospheric communication conclusions and references. Ionospheric communications. But what we learn in ionospheric communication is stated in the introduction sections. Introduction. In the study, which is a term paper on electronic sources and systems. Ionosphere communication systems, ionosphere and radio communications, effect of ionosphere on frequency, used areas of ionospheric communications, effect of ionosphere on communications, research on ionosphere and ionosphere communication, factor affecting ionosphere change and effect of ionospheric distortion. It is described in these signals. Abstract. The ionosphere is the upper atmosphere region that contains a sufficient amount of charged particles. Also called plasma. In the ionosphere, electrically charged particles formed by the ionization effects of X-rays and ultraviolet rays are found in the layers and layers. The amount of ionization in the ionosphere varies according to different times of the days and seasons. The ionosphere is a very important layer of the atmosphere for the propagations of radio waves. When radio waves propagate in the ionosphere, they are affected by reflections, refractions, absorptions, polarization, and scattering phenomena. Therefore, the ionosphere has a particular importance in which it affects the propagations of the radio wave to distant place in the world and directly affects radio wave communication systems. In civil and military shortwave applications, the ionosphere reflects radio waves and enables communication with distant regions. The ionosphere is important for the propagation of electromagnetic waves. In terms of shortwave communication, satellite communication and satellite-based navigation systems, ionospheric modeling is very important. Developing methods and algorithms to predict and minimize the effects of ionospheric disturbances and changes on communications. Ensuring that ionosphere information is obtained to support immediate and future predictions. Although GPS, a highly accurate position system, was originally developed for military use, it has found many applications in daily life thanks to advances in technology. In addition, the ionosphere electric density can be determined. The ionosphere total electron contact can be examined and ionospheric irregularities can be detected by GPS. Ionospheric communication. What is the ionosphere? In the upper parts of Earth's atmosphere, there is ionized gas layer with a Higgs electron density starting from an altitude of about 40 and 60 kilometers. This natural plasma layer, which was predicted independently by Heaviside and Cannell in 1901 and was called the Heaviside layer for many years, caused research to become more interested in this area as a result of Marconi's observation of the radio signals broadcast in London, Nova Scotia. The natural plasma layer, called the ionosphere, is formed as a result of the observation of ultraviolet rays from the sun by atoms and molecules. In the upper layers of the atmosphere, these layers can be formed as a result of photoionizations. as well as by the effects of strong electric fields and shock waves carried by lighting or very high temperatures. This ionosphere layer, which contains free electrons and plus ions, reflects electromagnetic waves, allowing these waves to travel quite long distances. Charged particles are trapped by the Earth's magnetic field. The height and properties of ionized layers depend on the nature of solar radiation and the properties of the atmosphere compositions. The ionosphere layer, which starts at an altitude of about 60 and 100 km from the Earth, reaches its maximum electron density and altitude of 250 and 400 km. The ionosphere layer is examined by dividing it into 4 sublayers according to the amount of ionization they contain. Layer D starts at an altitude of 50 km from the Earth's surface and extends up to 90 km. Ionization starts with high energy X-rays, and the amount of free electrons increases as the height increases. Layer E is at an altitude of 90 km to 150 km. Ionization in this layer is greatly reduced at night time. It creates a diffraction effect on the signals. Layer F is located at an altitude of 150 km. While this layer is a single layer during the night, it is divided into 2 layers. F1 and F2 during the day. The ionization intensity of the F1 layer depends on the angle of the sun, and it absorbs the high frequency waves passing through the F2 layer. The F2 layer is a highly variable layer with the highest ionizations. Its length and intensity varies with time, season, and sunspot activity. The highest electron density in the F2 layer and the electron density decreases as you go higher or lower. Figure 1, layer structure of the ionosphere. F1 layer and F2 layer you see here, and night F and E layer and F layer. And then effect of ionosphere and electromagnetic wave spread. The refraction of electromagnetic waves that traverse the ionosphere required and detailed study of the electromagnetic waves propagations in the ionosphere. The refraction caused by the ionosphere varies depending on the frequency of the advancing waves and the electron density of the ionosphere. The electron density of the ionosphere varies continuously depending on the solar events location. Solar events occurring in the 11-year cycle of the sun, season, time of day, latitude and longitude signs the wave propagation in the ionosphere will be delayed due to the refractions that occur. In order to determine this delay, the refractive index in the ionosphere and the parameters of the refractive index must be known. While calculating the refractive index, which is one of the important parameters defining the ionosphere. The properties of the medium and the waves should be known. For this reason, it is thought that the wave first travels in an environment consisting of electrically neutral gas and ions. The most important factor affecting the propagation of the wave in such an environment are the electron density, the external magnetic field B, and the collision frequency between the electron and other particles. However, the refractive index of the medium also depends on the characteristics of the wave. It also depends on the wave frequency, the direction of propagations of the wave, the direction of the electric or magnetic field vector components of the wave. Global Position System and Ionosphere. Global Position System is GPS. Global Position System is a communication system that enables positioning at any locations and time. It was developed in the 1960s by the U.S. Department of Defense in order to locate military vehicles or aircraft. The GPS system has become open to civilian use in our daily life thanks to the technological developments in recent years. It is widely used in vehicle tracking system, activate control networks, development of geographic information system, databases, tourism, agriculture, forestry, sport files, and hydrographic measurements. GPS technology contributes significantly to modeling to the ionosphere and troposphere. GPS measurements techniques which have a accurate position system and have many applications area. Also have weaknesses. The basic function of GPS location determination is to determine the distance between the satellite and the receiver. During the determination of the distance, error sources such as satellite ephemeris errors, satellite clock errors, ionosphere delay effect, troposphere delay effect, multipath effect are present. A careful study is required to eliminate these errors in studies requiring accuracy. The signal broadcast from the GPS satellites reach the GPS receiver located on the ground surface, first passing through the ionosphere and then troposphere in the Earth's atmosphere after crossing the space. Therefore, the ionospheric delay caused by the ionosphere should be determined very well. However, the structure of the ionosphere has a constantly changing structure with the effect of the time of day or night, season, year, latitude, and longitude, depending on the activity of the sun. Therefore, as the GPS signals pass through the ionosphere, they will be affected by the constantly changing structure of the ionosphere. Since the ionosphere has a feature of scattering radio waves, it will create a decrease or increase in receiver length. In order to overcome these disturbing effects, the ionosphere layer through which the GPS signal pass must be well modeled. The ionospheric effect is directly related to amount of the free electrons in the area along the path to which the signals has traveled. Role of ionosphere in radio communication. The ionosphere plays a great role in broadcasting, ship and aircraft communication and navigation by reflecting the radio signals back to the receiver. However, its effectiveness depends on the frequency of transmitted signal. This is critical because the behavior and the ionosphere often show marked difference during day and night. Moreover, it's known for changing its behavior during the different season. What is relieving, however, is that the variation are regular and may also predicted. These predictions help in the planning of the radio service. The propagations of the radio signals is influenced by the dispersive nature of the ionospheric plasma, and refraction of a signal depends on the wave frequency. The refractive index according to the Appalachian Hartree formula is this formula here. This equation is here. The expressions in the formula are as follows. Ne electron density, F Ne electron plasma frequency, F radio frequency, E electron charge, E0 the electric constant in free space, B the flux density of Earth's magnetic field, M electron it represents its mass, theta the angle between the direction of travel of the incoming wave and the magnetic field. Fp the speed of collision of the electron with large particles. Fh and the electron rotation frequency. Electron rotation frequency is typical 1.5 megahertz, while plasma frequency does not excite 30 megahertz. The collision frequency is around 10 over 4 hertz. With the approach made using this information, the phase refractive index is as follows, and P equal to these equations, or mg equal to this equation. The relationship between the x value and the electron density and frequency is these equations. Value is x Ne band mostly affects the movement of electrons, as ions are about 1,800 times heavier than electrons. Equation of motion under the influence of electric field for a signal electron of mass, velocity, and charge. These equations, mass time derivative of speed with respect to time equal to this equation. The further form is written as follows. These equations. When the number of electrons per unit volume is n, the induction current in the ionized gas is given as follows. These equations, Joule equals to these equations. From Maxwell equations, it is a Maxwell equations. Electron collide with neutral ions and molecules in the lower layers of the ionosphere. In this case, it is necessary to add the collision attenuation force mv to the force equations due to the conservation of momentum. The relative dielectric constant is the complex number when the collisions attenuation force is added. The relative dielectric constant is the complex number where the impact attenuation force is added. These equations. The propagation constant for a plane wave in an ionized gas is follows. Ionized gas constant, it is electron density in the ionosphere is a function of height. Therefore, a plane wave entering perpendicular to the ionosphere travels up to the height at which the electron density makes. In the plasma, after this point, progress stops and the wave is reflected back to the world. In case of incidence, the beam travels up to the height of ER in root equals to sin W, and then it's completely refracted. In the relationship between the frequency of the wave and the electron density and angle of the incidence, the upper limit for reflection is found as NC equal to F square times cos square W divided 81. The frequency that makes E0 equals to 0 for a given N max in the case of right angle of incidence is called the critical frequency. Critical frequency equal to 9 times N max in root. In the case of angle M max, the next equation, it is the equations. And the maximum value of secant WF in this equation is known as the maximum usable frequency. The upper limit of the UF usually does not exceed 40 megahertz. In the low solar activity period, the upper frequency limits is 25 to 30 megahertz. In ionosphere HF communications, MUF values are very important in link planning. One of the most widely used PKH programs for planning is HF. This PKH program predicts the basic parameter of point-to-point communications channels, an important variable for the ionosphere. If the propagation directions of incident and reflected waves are extended to a peak, the height at which they intersect is called the vertical height of the ionosphere. This height is the apparent height where the reflection is the vertical elevation angle of incidence is important in determining the maximum value of W and the maximum jump distance. The horizontal jump distance is determined as follows. These equations. Jump distance is here equals to W value corresponding to this distance is calculated as tan W equal to H derivative divided D divided 2 equals to Earth's magnetic field plays a very important role in ionospheric propagations at frequency below 5 MHz. The magnetic field of the Earth obligates the ionosphere to be directional dependent and expressed as a matrix of the effective relative dielectric constant. There are two propagations models in direction-dependent plasma. Ordinary and unusual, the plane wave entering to the ionosphere is divided into two as ordinary and unusual. The mode can combine and arrive at the receiver in this way. This is the main reason for the multipath and fading problems that occur with ionospheric HF shortwave communications. Since the electron density of ionosphere is a function of time, frequency and location, ionosphere channels also change with time and location and derivatives of time and positions. This multipath fading communication channel that changes with time, location, frequency, and time and position distortion requires spatial design of transmitters and receiver in these situations that require broadband and high data rate and channel capacity. This issue still a subject that is being studied intensely at frequencies above 40 megahertz. The directional dependency and the ionosphere retroflections feature repeatedly lost their effect. The ionosphere is direction independent as the frequency is above the high highest plasma frequency. The effect of the ionosphere on VHF and UHF and above communications decreases with the increase of frequency and is the direction deviations for satellite signals due to time delay. Phase phase oscillations and frequency-dependent refractive index. Factor causing ionosphere change. The number of electrons in the ionosphere varies due to activities such as solar flares, sunspots, and the Earth's magnetic field change. The ionosphere shows different structure in high latitude, mid-latitude, and regions close to the equator. Ionosphere variability is mid-latitude is less. Factors that cause change in the number of electrons in the ionosphere layer can be shown as events that cause magnetic field change such as solar activity, ionospheric storm, sunspot, geomagnetic storm. Ionospheric storm areas from sudden and severe distortions in the Earth's magnetic field and are caused by the complex interactions of a solar indicate plasma density with the Earth's magnetic field. Sunspots are relatively cold magnetic anomalies that occur in the photosphere layer of the sun. In the sunspots where the cold occurs, the loops of the magnetic field go beyond the convection layer and come out of the photosphere. Since the electrons in free form in the ionosphere are exposed to ionizations by solar radiations. The ionizations of free electrons is intense during the day and the ionizations level decreases at night. As a result, the number of electrons in the ionosphere change periodically depending on the influence of the sun. Apart from daily changes, seasonal changes are observed in the ionosphere due to the change in the angle of incidence of sunlight with the rotations of Earth around the sun. Sunspots are formed with an 11-year cycle. The ionosphere is also affected by the solar cycle. Since the ionosphere contains electrons due to its structure, it is affected by magnetic field change, and the magnetic field changes that occur on the Earth also affect the ionosphere. Earth's magnetic field changes depending on the movements of the moon and the sun around it. The ionosphere varies according to three main effects, namely magnetic changes due to movements of the sun, moon, and Earth. Total electric content, TEC. TEC is one of the important parameters expressing the characteristics of the ionosphere and used to examine the structure of the ionosphere. This equation gives TEC. Integral of NE with respect to L. The unit of TEC, which is also interpreted as the total amount of free electrons along a cylinder of 1 meter of square section is TECU. 1 TECU is 10 over 16 EL divided square meter. By examining TEC values, short and long-term changes in the ionosphere can be followed. In addition to theoretical and empirical models, there are various ground-based and satellite-based techniques for ionosphere studies and TEC estimations. Ground-based techniques include ionization, backscatter radar, and stage-incompatible backscatter radar. The common feature of these techniques is to conduct examinations by sending radio waves to the ionosphere. These signals sent from satellites are also used for the TEC studies in the ionosphere. Some of these satellite systems are Earth Position System, GLONASS, and TOPEX Position System. Geocentric techniques for ionosphere study. It's one of the best methods to send radio pulse signals up from the ground to determine the height of the ionosphere. However, calculating the return time of the sent signal with this method is not suitable for finding the actual height. Because the sent signal moves slower in the ionosphere layer than on the ground, it is a function of electron density and magnetic field. Since the group refractive index of the ionosphere is greater than 1, the apparent height is always greater than the true height. Ionization sends a high-frequency signal to the ionosphere, and measurements are taken by increasing the frequency of the transmitted signal. The time between the sending time of the beacon and the time to return is measured. As I mentioned earlier, due to refractive index of the ionosphere, the height measured is greater than the actual height. The closer to the plasma frequency the measured height becomes infinity. This is because the sign crosses a finite height with zero speed. A relationship can be established between the height of the ionograms measured and the frequency of transmitted signal. With ionograms, visible ionospheric heights and critical frequency can be calculated. When the probe sent radio waves to the ionosphere from an oblique angle, the radio waves in the form of a short pulse train are diffracted in the ionosphere and scattered irregularly. Scattering occurs in two different ways: direct scattering and scattering by reflection from the ground. In case of direct scattering, the signal reaches the receiver in the same way. In case of In case of direct scattering, the signal reaches the receiver in the same way in case of scattering by reflecting from the ground. In the RF signal reaches the receiver first by reflecting from the ground and then from the ionosphere. Direct backscatter mode issues are used to detect distortions in the aurora region. Phase mismatched backscatter radar is the most powerful ground-based technique used to study the ionosphere. The technique is based on radar. A radio beacon is sent towards the target and the reflected signal is analyzed. In this method, the target is the electrons in the ionosphere. Since the amount of energy emitted by each electron is known, the power of returning signal indicates the amount of electrons, thus the electron density. The width of the spectrum is a measure of the temperature in the ionosphere. This temperature can be different for the ions or electrons. Some known example of phase in some backscatter radars and their countries. Arecibo, Japan, Isket, Sweden, Norway, Finland, Irkutsk, Russia, Milton Hill, United States. MU Japan can be shown. Satellite and other methods. YTX, TOPEX, Poseidon, GLONASS are based satellite methods. Ocean Topography Experiment conducts ocean study as a joint venture of NASA and the French Space Agency. TP satellite is located at an altitude of 336 kilometers. There are single and dual frequency altimeters on the satellite. With the dual frequency altimeter, proper TAC measurements can be made on the ocean. TAC values obtained by TP are compared with TAS values obtained by other methods. Faraday rotation is also a method used in ionosphere studies. When linearly polarized radio waves interact with the Earth's magnetic field, the polarization plane of the different wave rotates. One of the wave is called normal and the other abnormal. Faraday rotation is direct with TES and magnetic field strength. Inversely proportional to the square of the frequencies in the magnetic field strength is inversely proportional to the cube of the distance. Faraday rotation cannot be used in TES calculations for altitudes above 2000 kilometers. Electron density above 2000 kilometers is already negligible. The upper probes are small probes carried by the Earth's moons. Since approximately 2 divided to 3 of the total electron content of the ionosphere is the upper ionosphere. The upper ionozones are of great importance. The two techniques used to examine the upper layer of the ionosphere are the upper probe and the phase incomputable backscatter range. Ionosphere models and indexes. The ionosphere models can be divided into two categories as theoretical theoretical and empirical models. Empirical ionosphere models are obtained by the parameterizing long-term information about the ionosphere, parameterizations according to solar activities, seasonal change, geographic latitude, longitude, and local time change with a long-term data set. Some empirical models have been developed according to different geographic area, solar radiations, and geomagnetic conditions. The most well-known of these models are the band ionosphere model and the IRI model. Band's empirical ionosphere models expresses the electron density in the ionosphere as a function of latitude, longitude, time, season, and solar radiation. The model was applied between 1962 and 1969 using 50,000 upper ionograms and around 400,000 bottom ionograms. One of the most used empirical models is the IRI model, applied in 1978. Updates were made to the IRI model in 1986 and 1990, 1995, and 2000. The IRI model is continuously being developed with support of the Space Research Committee and the Radio Sciences Associations. The largest data source for IRI is the spherical ionosphere network, powerful backstar radars, ISIS, and the allowed upper probes. And then this is the last subject, research and development study. To reveal the effect of ionospheric and plasmospheric environments on the terrestrial and Earth space communication, especially considering the recent past. Current and future prediction models will be made on software. Tools will be developed for GNSS. The application will be very useful in examining the properties of the ionosphere's high-order effects on communication. The control of the upper atmosphere is based on the present and future prediction. The performance, the present and future prediction procedure. The studies are also based on the foundation of increasing the performance and robustness of the prediction techniques. Dynamics modeling will be discussed in the future analysis. The new ionospheric and plasmospheric data obtained have been obtained for current and future applications. The activity is to establish a basis for establishing a network that will provide higher monitoring of ionospheric and plasmospheric measurements and other SunGrant parameters suitable for the space environment. GPS, GLONASS radio overlap measurements provide important findings for the global study of the Earth's ionosphere and plasmosphere systems. By LEO satellites with GPS-based realizations of the total vertical electronic measurements, circular peripheral examinations data, and tomographic solutions can be obtained to obtain the dimensional structure of the ionospheric electron distributions. The effect of temporary solar events such eclipses on communication will be measured and analyzed. And then conclusion. The ionosphere is the ionized gas layer of the atmosphere, thus providing signal transmission. Since the ionosphere consists of ionized gas, change in the ionosphere directly affect signal transmissions. Electron density in the ionosphere is very important in signal transmissions. So electron density TAS measurements are made. The different values of the TAS affect the transmissions there, so the signal transmissions varies in different parts of the world. Ionospheric communications include the communication systems such as radio and GPS in the world. Ionospheric communications is the basic mechanism of many devices in the world. So there are continuous studies on this subject. Basically, I explained ionospheric communications. Thank you for listening to me. You can use the researchers below for more informations. These references you use.